you had a good weekend? Sorry I wasn't here Friday, but I was in Toronto. So I guess last time we did some partial fractions, but maybe not enough. Is that right? Should I go over some more? Okay. All right. So let me just do a couple of examples. So the situation is where we have something. We have something like this. Oh no, this one's easy, isn't it? Oh well. Say we have something like this anyway. Yeah, that was a stupid one. Oh well. If we have something like this, then what do we do? Well, so here, why don't we... partial fractions, we get something like the integral of here's that, b Okay, so let's do that very easy question. Oh no, let's add a C. D. Most of the people liked this option, something like 75%. And then this is number 2. Not too many people liked this one. I don't know why not. And nobody liked trig substitution. In fact, all of them work. It's just that if you do the substitution, so let's do the substitution first. So here, if I make the substitution, obviously I want to let u equal x squared minus 1. I don't know if that's obvious to you, but it's completely obvious to me. And then du is 2x dx, and I almost have an x dx sitting around there. I have that 3, but so what? So if I do that, then I have x minus 3, x squared minus 1 dx is, so then this will be, I put this part, and then I have the 3 left over. So actually, let me leave that in. So I have that. And now this I can do easily with this substitution. So this is 1/2 u, because x dx is 1/2 du. So I have a 1/2 du on the top and a u on the bottom. And then here, this is one I should know. Well, I guess this does matter, right? Because now here I have to do this 3 over x squared minus 1. This is not 1. I mean, now I can make a trig substitution, I suppose. But I don't want to do this, right? To do this, 1 over x squared minus 1, I have to make the substitution of secant squared. I don't know. This is ugly. Is this ugly? Yeah, this is ugly. Right? I mean, this I would have to do by a trig substitution. So I don't really want to go here. Is this ugly, or am I just asleep? It's ugly, right? So so I make a secant, and I get a secant squared. Integral of, well, that's cosine squared, and then I have to do 1/2 cosine. Yeah?
You still can't plug in u to that?
Here?
Yeah, squared minus 1. You still have u.
No, no. So if I do 3 over u, then I have left over, I need an x. So I need some x here. To change du into dx, this would be 3 over du over 2x. But that's not so good. Yeah. So I can't just plug in the u, because I have to deal with the dx. So this I would just leave. And now I'm kind of stuck. I mean, here if you have this, you can do this. So I can use a trig substitution that secant squared x is let's call it, no, sorry, secant squared of theta is x, and then I get the integral of a cosine squared, and then I turn that integral into cosine squared with a half-angle formula, and it's just, it works, but actually maybe I shouldn't be sad, I should be like sweating. It's a sweat. So, it's here. Anyway, you can do it and it will eventually get there, but it's not the most efficient manner. So, formally the correct answer is either A or B and C together, and depending on how much of a masochist you are, it either doesn't matter or it does. I mean, it matters in the sense that you've got to kill yourself to do something that's relatively easy. So let's do it the easy way now. So the way that most of you want to do is we just use partial fractions. So just to remind you, I just need to solve the little algebra problem, a over x plus 1 plus b, yeah, that's what I wrote, over x plus 1 equals x minus 3 over x plus 1 times x minus 1. So I want to solve this little algebra problem and figure out what a and b are. And I can either do this by cross-multiplying and getting two equations. Yeah, let me do that. So this is the same thing as if a times x plus 1 plus b times x minus 1 equals x minus 3. Right? Because if I find a common denominator and I get that. And now here, I can either say, all right, looking at this, a plus b has to equal 1 because the coefficients match. So I'm going to do this two ways. Did you do it both ways? No? Okay. I don't know. Okay. So I'm going to do it both ways. You choose which way you like. They're the same to me. So either I can say, all right, if I clean this out, I have, there's a 1 there, ax plus a, but I'm going to not worry about that. Let me leave the x off, in fact. A plus b has to equal 1 because the powers of it, the coefficients of x, a plus b, have to match. And then the coefficients of the constants, a minus b, have to equal minus 3. So this is from the x, and this is from the units. And then I solve, that's a 3. It's just a funny looking 3. And then I solve those simultaneously. So if I add those things together, I get that 2a equals minus 2. And so a equals minus 1. And since a plus b is 1, that means b is 2. So that's one way I can do it. An equivalent way I can do it is I can look at this equation and I can say, okay, this equation has to be true for all x's. So in particular, this equation has to be true. This equation has to be true when x is 1. If x is 1, then this is 0 and it's gone and it's out of my face. So that means that a times 1 plus 1, so that's 2a, equals 1 minus 3. Maybe I should write it as 1 minus 3. And so that means, again, a is 1, negative. Because 2a has to equal negative 2. And if x equals negative 1, which kills this piece, then I have here negative 2b equals negative 1 minus 3, negative 4, so that means b equals 2. These are the same, just done in a slightly different way. I mean, what's making them work is exactly the same fact, which is that this equation has to hold for all values of x. So either you can equate coefficients, or you can pick suitable values of x, and whichever one makes you happy is fine, because they're really the same. All right, so but in both cases, we wind up with something fairly easy. So that tells me that a is negative 1 and b is 2. So that means that the integral x minus 3 dx over x plus 1 times x minus 1 is the same thing as the integral of negative dx over x minus 1 plus the integral of 2 dx over x plus 1. And this is really easy. Right? So this is, I need to look at it. This is the, if I make the substitution u equals x minus 1, then I get 1 over u. So this is minus the log of x minus 1. And here I make the substitution u equals x plus 1, so I get 1 over u. So this is plus 2, the log of x plus 1, plus the constant. Okay? So these are really easy once you get the hang of them. The hard part, so the hard part with partial fractions, actually, as in most of calculus, is not the calculus, but the algebra. But this is pretty straightforward. Any questions on this at all? Then why did you make me do it? Okay, so then let's just go on. Let me do another one. So, unfortunately, and I think this is what she did at the end of the class, that at least she told me it confused you all. Maybe all the factors are not linear. Maybe I have a power on the top or the bottom, or something like that. And I can't factor it into linear factors, because I can't always factor everything into linear factors. So the problem here is, well, let me just do an example still. So say I have the integral of 3x squared minus x. See, I worked these out in advance. So 5 over x minus 2 squared plus 1, and there's a dx here somewhere. And again, it should be pretty obvious that what I really want to do here is partial fractions, because okay, so now I want to be able to split this up. The problem is, so let me actually move over to the next board. So I have this problem, 3x squared minus x plus 5. x minus 2 squared x plus 1. And I want this to be equal to something over x minus 2 squared plus, I'm going to skip b because I'm going to use it in a second, over x plus 1. But this won't actually work because I'm going to be missing an x. This only gives me a linear term in x, and it doesn't give me full choice on the x term. It gives me full choice on the constant term. I mean, the constant and the x term are related by that. So I need a slightly more complicated numerator here so that I have the full freedom to vary the coefficient of x. Well, this is really the coefficient of x squared and the coefficient of x. Because when I cross multiply, this one gets a quadratic term, this one gets a linear term, and I lose out on the freedom. I need 3 things to vary because I have a quadratic polynomial or a cubic polynomial, so I need 3 degrees of freedom. So the general rule is, or at least some people say it slightly differently, when you take your factors, you always put the numerator so the numerator is always a polynomial 1 degree lower than the denominator. And then maybe I can split this up. Now, those of you that may have seen this before, or the way they describe it in the book, they say, okay, take a over x minus 2 squared plus b over x minus 2 plus c over x plus 1. Those are the same, which is slightly different choices of a, b, and c. But the advantage of doing this is this unifies the 2 second cases. Okay? Any questions on that at all? Yeah.
Does it matter which letter is assigned the x value?
No. Would you like to make this be a b and this be a theta? I mean, it doesn't matter. Now you can't read it, so that's probably a bad idea. The letter, I mean, we can put a smiley face here and a star here. It doesn't matter because it's just a placeholder. So use whatever letter you want. But then once you start, be consistent. You understand?
Yeah.
So what matters is that the thing on top of the quadratic term is a linear polynomial, and the thing on top of the linear term is a constant. Right? You wouldn't leave it with smiley face and star? Yeah. Okay, you like smiley face and star, we'll keep it. Alright, so now we can use the same trick. We just cross multiply and come up with something. So when we cross multiply, we're going to get smiley face x plus star times x plus 1 plus c times x minus 2 squared, and that has to equal that 3x squared minus x plus 5. And so now we need to figure out what smiley face, star, and c are. And again, we can use either method. Let's just equate coefficients this time. So if I equate coefficients, well, let's see. Yeah, let's equate coefficients. So otherwise I'll have to choose 2 values of x. Doesn't matter. So here, if I multiply this junk out, I get smiley face x squared plus smiley face plus star times x plus star plus. So I'm just distributing this. It's confusing because I'm not using actual letters. Leave it! No! Okay. Sorry. And then here I have to square this out. So this squares out to be x squared minus 4x plus 4. And when I multiply that by c, I get that. So this is cx squared minus 4cx plus 4c, and that has to equal 3x squared minus x plus 5. And so from there, now we can match things. So the x squareds give me a 3. So I have Smiley plus c equals 3. And the x's tell me that Smiley plus star minus 4c equals minus 1. And then from the units terms, I get that star plus 4c is 5. And so now I have to solve these things all together. I should have done it the other way. I think they did in my office. Oh well. So if I add these together, that sucks. So if I add these together, I get, so adding this one and this one give me smiley face plus 2 stars equals 4. And did I make a mistake? Somebody's telling me I made a mistake. Where? Yeah, you have a question. Okay, so let's go through this process again. I look at this equation here. I cross multiply everything, I get some long mess. Now, what has to be true, this is what's in front of an x squared. In front of an x squared, I have one smiley face, I have a c, and I have a 3. And this is what's in front of an x. In front of an x, I have a smiley added to a star. I have a minus 4c. And I have a minus 1. And this is what's in front of a 1. In front of a 1 here, well, that has an x. In front of a 1 here, I have a star. And I have a 4c. And on this side, I have a 5. So that gives me my 3 equations. And now I just want to say, if I have 3 numbers that when I add up in this way, if I have 3 numbers, they have to satisfy these 3 equations. And now I want to solve these 3 equations. Maybe I should do it the other way, right? If I do it the other way, then it tells me C right away. So let's look at the other way. So you can solve these 3 equations, you'll probably get the same answer I will the other way. The other thing I can do is I can say this has to be true for all x's. If x is 1, then this mess here is 0. X is minus 1. Then I have smiley plus star times 0 plus c times minus 1 minus 2 squared equals some number. 3 plus 1 plus 5. So this is gone. And this is 9. So I get 9c equals 9. Well, that's good. So that tells me right away that c is 1. Now that I know what c is, then I can go back and figure out what smiley and star have to be. if I take x to be 2, well, that gives me a relationship between Smiley and star. So actually, I'm going to mix these two methods. So I know that c is 1, which makes my life a whole lot easier because I know that Smiley, now he looks a little sad. Oh well. Smiley plus 1 is 3 from this line here. So since Smiley plus 1 is 3, that means Smiley is 2. And since Smiley is 2, and here I know that c is 1, so star plus 4c is 5. Star plus 4c is 5, so that means that star is 1. So now, mixing the two methods actually turned out to be the most efficient way. You can, of course, solve these by adding and subtracting and mushing them around. It's fun. It works. And you can, of course, use this method exclusively as well. Yeah? Would you like to have d over x minus 2? d will be 0. All right. So let me finish this and then I'll address that. Okay? So are we okay on this? So use whatever method works as long as it's legal. That's fine. I'm mixing the two methods. They're the same method, so it doesn't matter. This all comes down to the fact that if two polynomials are equal, they have to be equal at every x value, and their coefficients have to be equal. If two things are equal, they have to be equal, so that means they have to be the same. So I can use their various aspects to identify them. If you're trying to identify your mother, you can listen for her voice or you can look at her face. They're the same. They're both ways of identifying who your mother is. Okay, so anyway, so we have this, and so now this problem becomes easy somewhere. I guess it will be easy over here. So that means that the integral of 3x squared minus x plus 5 dx over whatever all that junk is, x minus 2 squared x plus 1 is the same thing as the integral, I've lost who's what. Smiley is 2x plus 1 over x minus 2 squared dx, and c is 1 dx over x plus 1. And then this guy you can do by substitution, and this guy is a log, so away you go when you stop there. So let me just not do that. Now let me come back to somebody over here, I think in the blue, right? Yeah. So her comment about why don't I use D instead? Because it's the same. Let me use D on that board. So if you like, if it makes you happy, I could write this a different way. I could say instead that 3x squared minus x plus 5 x minus 2 squared x plus 1 is a over x minus 2 squared. Well, let me, I can use those. B over x minus 2 c over x plus 1. I can do that too. Is that what you get? No? Forget it? So I can do this as well. It's the same. Because if I put these things together, then my B will just be some combination of smileys and stars. Right? Because so A is the same as smiley, and B is a smiley and a star, which is B plus A, B plus minus 2A is a star. I'm sorry? Oh, yeah, yeah. Okay. Sorry. But it's still the same thing morally. So, the A is the star, and, B is the smiley, and A minus 2B is star. So, that doesn't matter. And if you want to put more stuff up here, if you want to put D's and E's and Q's times X's and X cubes, it's fine, but they'll all be 0. So why bother? So that, yeah. What else would it be? Okay, so if I tried to do X minus 2 and X plus 2, then I wouldn't have a way of... You mean you would like this one to be like that? Is that what you're asking? Okay. So, this is a good question, and it's something that confuses people all the time. Imagine that I did that. So, imagine that I wrote okay, so let's do a simpler example. Okay. Suppose I did that. Suppose I wrote A over X minus 2 plus B over X minus 2. How can I get an X squared out of that? I can't. But that has to equal something with an X squared. Right? Because I have an X squared on the top. I can't get an X squared out of that. Because when I cross multiply, I'm going to have A times X minus 2 plus B times X minus 2. Well, they're not going to get a square. So it's not going to happen. So I need to have something squared. So I could square this, and then when I cross multiply, the B will get the X squared term. But somehow I'm going to have to pick up the X squared term. So the general situation is that whenever I have something for the factors, well, this is, that's bad. Whenever I break this down, the thing on top is always a polynomial of just 1 degree lower of the thing on the bottom. Now, sometimes you might have to, like in this example actually, you might have to split it up. Because when I make my substitution, it's not going to quite work, but I can split that out. You see that? Okay. Yeah.
So if you had an X minus 2, you have AX squared plus BX plus 2.
Right. So if I have the integral of X minus 2 cubed times X over, I don't know, an X, say. So I want to split this up. Then I'm going to write this as A over X minus 2 cubed. I can either write it as 3 things, where I do a 2, a 3, a 1, or I can just write it as one thing. Like that. And since I put an integral there, I got it in right here. Yeah?
With the partial derivative, we have a lot of things that
Yeah?
and on top of that, with all the other smiley faces and stars and
Yes?
stuff like that, are you solving by elimination?
So, okay. I am solving by elimination, yes. So I can solve this by elimination. But I have extra information that I might as well use. I don't like solving 3 equations and 3 unknowns because I combine this and I combine that, and now I get 2 equations and 2 unknowns, and then I solve the 2 equations and 2 unknowns, and then I go back and find the other one. it's easy for me to figure out what c is not using this. So by looking at the equation here, that if x is negative 1, this term is gone. When x is negative 1, this thing is 0. And then I have 3c, or negative 9c equals 9. So by a judicious choice of x, I can make the equation simpler. I'm saying sometimes one method is faster than another. So what I don't like to do is say, always use this method because it's always best. It's not true. Sometimes one method's better, sometimes another method's better, sometimes a mix of the two methods are better. There are two methods, they're the same, really, but they seem different, and they have a different feel, and you use whichever one works best at the time. I can do this, I can forget about the other method entirely, and just solve this by itself. So if you're confused by the other method, forget about it. Just solve these 3 equations and 3 unknowns. You'll get the same answer. I guarantee it. But it's slow. It sucks. But you're welcome to do it. This other method isn't going to work so well here because I can kill the x squared minus 2 by substituting x equals 2, but then I'm left with something involving both Smiley and star. So I need to make another choice that will not kill all 3 terms and put that together. So instead of doing that, I sort of mix these 2 methods. They're all the same thing, so you can do it. Great. Okay, other questions about this? We will, I mean, it may seem like, this notion of partial fractions comes back. So, outside of doing integrals, it still comes up in other areas. So let me stop with this guy. Let me point out one other thing that will, more algebra, so really today is an algebra class. Suppose that I have something like, let me just do the same integral, x cubed minus 4x squared plus 1 over x squared minus 1. So let me forget about the integration part. Let's just ask an algebra part. So, suppose I want to do this. What should I do? Should I write this as So A, yes. B, no. There you go. I seem to have gotten a lot of people, so I'll stop there. Unless you need more. Wait, okay. So, by overwhelming majority, you think this won't work. And you're right. Why won't this work? I can't get an x cubed. So what do I do? I do what? I divide it. So, okay. It does come from the denominator. I mean, I can't start with partial fractions. I do something first. So the problem here is that the power here is 3, and the power here is 2. Right? If you prefer, I could write this as x squared minus 1. The power here is 3, and the power here is 2. Partial fractions is not going to work. I have to clean it up a little first. So this is the same thing. X cubed minus 4x squared plus 1, x squared minus 1. Those are equal. And so what I have to do is reduce the power of the numerator. So I want to get that down to being an x squared. Or, yeah. So, I mean, actually, yeah. So I need to do division. I need to say, if I multiply the bottom by x, I'll get an x cubed that I can subtract off. So I have to do long division here. I don't have to do it in exactly this form, but okay. I guess I'll leave room for x. And probably a lot of you forgot how to do long division with actual numbers. How many people remember how to do that? If I want to do like 15 into 20961. People remember how to do this from like 3rd grade? It works exactly the same. So when I'm dividing 15 into 2096, I say, okay, well, 1 goes into 2, 2 times, no, that's too big. So I better use 1 time, so I put a 15 here, I put a 1 here, I subtract, I get 59. And I say, how many times does 15 go into 59? 5 times, no. 4 times, no, almost. 3 times. And then I get 45, 3, and I subtract, and I get a 1, 4, 6. And then I say 15 maybe here, maybe 9, no, 8, and so on. And I just do this. 9, 9, 45, you're right. Okay, so 9 works, and when I do 9 into here, I get 90 plus 45 is 135. And a 1, 1, and I bring down the 1. I'm already tired, but now it's so close I should finish, right? So if I go 15 into here, it goes 4 times, 5 times. Come on. 7? 7's too big. 6. If I do 6, then I get 60 plus 30 is 90. 7. 105, and I have a remainder of 6. So I'm actually going to write it as a remainder of 6 rather than writing 6/15. But if you prefer, you can write it as 6/15. Okay, here the trick is exactly the same. I look at the x squared. I say, how many times does it go into x cubed? It goes in exactly x times. And so if I... Whoops. What am I doing? So it goes in, x squared goes into x cubed exactly x times, and then x times x squared minus 1 is x cubed minus x. And I subtract. Which is exactly what I did here. 15 goes into 20 how many times? 1 time. 1 times 15 is 15. Then I subtract this part. And then I bring down what's left over. So here I subtract. The x cubed is gone now. When I subtract here, I get a 4 minus 4x squared minus x plus 1. Plus, I subtracted the minus. Yes, thank you. And I can do this one more time. I can say, how many times will this x squared minus 1 go into minus 4x squared, blah, blah, blah? Well, x squared goes into 4x squared minus 4 times. So then I multiply back, just like I did over there. Minus 4 times x squared is minus 4x squared. If this term doesn't cancel, you screwed up. And then minus 4 times minus 1 is plus 4. 4. And then again, I subtract. Those guys cancel. X minus 0 is x. And this guy, 1 minus 4 is minus 3. So then, well, I can't put that one up. Okay. So then this problem becomes, so that tells me, oh, I guess I need the remainder. This is my remainder. If I try and divide x squared plus 1 into this, I will need to divide by x rather than multiply by x. So that means that this process has shown me that, where's my problem? That x cubed minus 4x squared plus 1 over x plus 1, x minus 1 is the same thing as x minus 4 plus x minus 3 over x plus 1, x minus 1. And so if I'm integrating that, so if I want to integrate this, then I integrate this, and I integrate this. And this one I did already at the start of the class. So I chose this on purpose to make sure it would come out. So now I can do this by partial fractions. Right? So let me not do this by partial fractions because I already did it. It's right there. So there, it's done. So for partial fractions to work, you need the degree of the numerator to be 1 less than the degree of the denominator. Because otherwise you can't pick up the extra term. So sometimes you have to rearrange a little. Okay, so let me finish this with, that's pretty much it for techniques of doing integration. So you now know as much as I do about how to integrate, but now there's some other variations on that which we'll focus on in the next portion of the class.